Okay, so we have the recording and the streaming started. Might as well get started with our session. Good morning, everyone. We're going to start out this morning with several talks on chemistry in the troposphere and stratosphere and aerosols. And then we will stop a few minutes before 11 for the CGD seminar. So the end of our session has a discussion session, but that's really only 5 minutes long. So hopefully people will leave a little bit of time after their talks, so we have time for questions because we won't have much time before the seminar. I don't think I have much more in logistics, so people can ask questions by raising their hand after the talks, or you can go ahead and write your questions in the chat. And then if we can't get to answer them in person, maybe the speaker can reply in chat during following talks. So since we have quite a bit in our schedule, I think we could go ahead and get started. Rafa, if you're ready, you can, I will stop sharing the schedule. And
thank you very much.
You can share your screen. So Rafael Fernandez will talk about some very short-lived halogens in CSM, coupling oceanic emissions to the stratosphere. That looks great.
Thank you very much, Luisa. So thanks a lot for inviting me once again to talk here in the NCAR workshop. Last year, I made my presentation and I focused, I think, too much on Fortran routines, username list options, and technical things, and didn't get time to talk about a little bit more about the implications. So this year, I focused a little bit more on this. So just to put it into perspective, all the developments we've been doing regarding very short-lived chemistry in Chem. So since the initial papers published by Alfonso's group in 2012, we have implemented very short-lived halocarbons emissions, the Ordóñez et al. Inventory. We have developed a quite complex gas phase, but also heterogeneous phase chemical mechanism, which is implemented in the model now. We have validated oceanic halocarbon sources, but also inorganic reactive halogen species like BRO and IO, and for sure ozone with observations from different platforms. We here on the right, we can see this is one of the initial estimations of how large could this natural halogen-induced change in ozone in the troposphere, and the first estimate of the radiative effect of these ozone changes. And for sure, we have cooperated with many other groups trying to develop and advance in the implementation of these processes in other models. So today's talk, I will focus on iodine mostly because Carlos' talk, which is next to me, is also focused on iodine. And I thought this could be a nice introduction for that. And I will try to go into these initial 5 steps, trying to point out differences between organic and inorganic sources of iodine. Also understand the change in partitioning between iodine reactive species and reservoir species between present and pre-industrial times. Understand or present the geochemical feedback mechanism we suggested for the interaction between tropospheric ozone and iodine emissions. Also projecting to the future the evolution of the impact of natural halogens into the evolution of ozone, and present just a very short slide on the gas to particle conversion, which is important to understand the presentation by Carlos. So for those which are more familiar with bromine and chlorine short-lived species, So the model has included the Ordóñez et al. Inventory of bromocarbons and chlorocarbons emitted from the oceans, which follow chlorophyll A maps. And for bromine and chlorine, they have longer lifetimes. The importance of source halocarbon source gases is important for the free troposphere. But for the case of iodine, even when we had implemented very short-lived emissions of halocarbons like methyl iodide, we were not able to reproduce observations of inorganic iodine species in the lower in the marine boundary layer, basically. So we needed to add a fixed input of inorganic sources, but could not really explain why was that the reason. Later, the group of Lucy Carpenter, they developed a parameterization which indicated that the flux of inorganic species from the ocean, of iodine species from the ocean, was driven by the deposition of ozone and the oxidation of aqueous iodide occurring at the sea surface interface. So the concentration of iodide was parameterized and found to be dependent on sea surface temperature. And that's also explained in the McDonald paper. And what we did was to implement that in the model and get the model ozone, surface ozone levels, get the aqueous iodide representation based on the sea surface temperature that we have in the model, and also to determine a wind speed mask to allow for the limits of where the parameterization was found to be important. And with that, we determined the total iodine flux, which was found to be close to 2 teragrams per year, which was what we initially addressed just to reproduce observations. And the most interesting thing was that we found that this iodine flux was really dependent on the total levels of ozone. So the dependence on the ozone levels is quite large, which will be evaluated in a couple of slides. So we also were interested on understanding, so IY is the total iodine mixing ratio among all the species, which can be split between reactive species and reservoir species. So if we look here in the top, is the ratio present day divided by pre-industrial times for knots, and this is for HOCH. And what we can see that this ratio is much larger than 1. And because of that, in present time, there is a larger fraction of reservoir species. So the dominant fraction of iodine are in reservoir species. So in the present time, we have larger iodine levels, but there is also less reactive fraction of that. So we need to understand these two things to evaluate how the iodine encasement affects the total ozone burden changes since pre-industrial times. So based on these ozone changes, so the top figure here presents more or less the iodine source flux from the ocean. And we know that iodine source depends on ozone, but there has been a really marked ozone increase since pre-industrial times, which also has a very important hemispheric difference. And so if the ozone has increased, then we found out that since pre-industrial times, the inorganic source gases has increased by up to 70%, and about 40% if we think of on the global scale. So the larger the ozone levels, the larger the iodine emissions that we have from the ocean. And that's what we found in the Prados Roman et al. Paper. So the most interesting thing of this is that if we have a larger iodine emission, which is driven by an enhancement in ozone, the higher iodine levels also destroy much more ozone. So since pre-industrial time, it's not only an enhancement in the iodine emissions, but also in the iodine-driven ozone loss, which has been increased. And this constitutes a very important natural chemical feedback, which has evaluated from pre-industrial time to the present and also moving into the future. Using the model, we have also evaluated which is the net contribution of iodine to the total ozone loss rate in the troposphere. Iodine is the second most important species in the marine boundary layer at the surface, and the third one if we consider the whole troposphere, and it's much more important than bromine and chlorine for tropospheric ozone losses. So one interesting result that we had and we could compare was to see if this increase in iodine source was observed in some records. So we compare with ice core concentrations that show that iodine levels in the ice core have doubled since pre-industrial time, and most interesting that have tripled since 1950. So using the model increase of ozone since 1950, we determine how much the inorganic iodine source was increasing during that time. And we found that during the 1950-1990 period, the increase in ozone, in pollution ozone in the northern hemisphere principally, has controlled the increase in iodine emissions. And then the retraction of the sea ice extension of the Arctic has also been important during the 1990-2010 period. And then just moving into the future, we performed some 21st century simulation projection from 2000 to 2100 with some predictions on how the very short-lived emissions could increase, the outgassing of these species could increase based on the CISCA paper. And what we found out is that even when for very short-lived halocarbons, the enhancement was always positive, then for the inorganic source gas, it depends on the scenario considered. So for RCP 6.0, we have a large increase on iodine emissions, but then for the RCP 2.5, this was smaller. The most interesting result is that regardless of the scenario considered, because of this natural feedback between ozone and iodine emissions, the net change of tropospheric ozone column remains almost constant during the whole century and reaches approximately 13% of the total column. This is just to highlight that these changes are larger on polluted regions, reaching up to 60–70% in the eastern US and up to 20–30% in Europe. And finally, just to understand some of the implications of iodine in the stratosphere, so we developed a different type of heterogeneous recycling schemes in the upper troposphere. Also some approximations that a fraction of these reservoir species can also be trapped into stratospheric aerosols and then be converted from the gas to the particulate phase. And with that, we were able to determine and to show that iodine might have a larger impact in the stratosphere than expected before. So I rather finish here, not highlighting any conclusions, but I'm open to questions to answer any missing points. Thank you.
Great, thank you, Rafa. Does anyone have any questions?
Luisa, I have one.
Yes, please go ahead, Doug.
Yeah, so Rafa, what do we know about changing emissions going into the future? You know, from you know, seawater changes, temperature and things like that for halogens in general.
Actually, what we based on what we read in the literature, So warming temperatures of the ocean may accelerate the Earth-sea exchange occurring moving into the future. But at the same time, many of these changes might decrease or reduce the net primary production occurring in the ocean, which is really important for the micro and macroalgal production of these halogen species. So this upper plot here of just for halocarbons is based on the CESM-AMWG paper, which based on, I think it was 1990-2007 observations, they determine a maximum rate of increase of up to 30% if we move into 20,100, if we assume this is constant. And then we computed these variations online based on the RC exchange and MPP reduction. We computed that online on this model. That's presented in Iglesias Suarez paper.
Thank you.
Anyone else? Well, if not, we'll maybe move on to Carlos's talk. People can be thinking of more questions. So Carlos Cuevas will tell us about the influence of iodine on the Antarctic stratospheric ozone hole.
Thank you very much, Lisa. I'm going to try to share my presentation. Can you see it?
Yep. Go into full screen.
Okay.
Oh, perfect.
Thank you very much. My talk is about the influence of iodine on the Antarctic stratospheric ozone hole, which is something that had been published just yesterday in PNAS. So all the details about this work and the presentations can be found in that manuscript. In the downline, I want to talk about the Antarctic ozone hole and iodine transport to the stratosphere. I will talk about the configuration, about the Antarctic stratospheric ozone depletion by iodine, and also about the relative importance of iodine compared to bromine and chlorine. The Antarctic ozone hole at the iodine transport to the stratosphere. As you know, the catalytic depletion of Antarctic stratospheric ozone is linked to anthropogenic emission of bromine and chlorine. Some problems with the but the contribution of ocean-emitted iodine to ozone hole chemistry has not yet been evaluated due to the negligible amounts of iodine that were previously thought to reach the stratosphere, which is approximately less than 0.15 ppts according to Bass et al. And according to the WMO report up to 2014. However, the detailed measurements of IO and particulate iodine in the upper troposphere and lower stratosphere, in combination with some modeling using Gangen, had indeed confirmed that 0.76 ppt for inorganic iodine, both in the gas phase and particulate phase, 0.56 ppt as iodide entered the stratosphere via convective outflow in the tropics. What we have done in this work is to use the specified dynamic version of the whole atmosphere community climate model, version 4, WACAM SD, to assess the currently neglected role played by iodine chemistry in the formation and evolution of the stratospheric ozone hole between 1980 and 2015, based on this recently measured range of iodine injections to the stratosphere. The model configuration is shown in this slide, and we have used the community system model CESM-1 with the whole atmosphere community climate model version 4, WACAM 4. This model setup is based on the specified dynamic version of WACAM, including reanalysis for temperature, zonal and meridional winds, as well as surface pressure fields from the MERA1. We have implemented in WACAM the very short-lived halogen scheme previously presented by Rafael Fernandez in his previous presentation, which include offline emissions of oceanic very short-lived of chlorine and bromine and hydrocarbons. We have included nano-like computation of sea-salt aerosols, the halogenation source due to effective uptake of chlorine and bromine from sea-salt aerosols, heterogeneous reactivation of inorganic halogen reservoirs on top of ice crystal in the upper troposphere, inorganic iodine salts from ozone-driven oxidation of aqueous iodide in the source, and a parameterization representation of particulate iodine, IPART, assuming that the rate of formation of this particulate iodine in the stratosphere is approximately 1% of the recycling rate of inorganic iodine in reservoirs of Purine stratospheric aerosols. Here are the stratospheric heterogeneous bromine, chlorine, and iodine reaction on different substrates, or liquid binary and ternary surface polar stratospheric clouds, or NAT and water ice polar stratospheric particles. The update confidence that we have employed for the reaction of iodine has been actually mapped from the equivalent reactions from bromine. Due to the lack of information in the literature. Here in blue, we have highlighted the reactions that we have included in the standard WACAN scheme. We have employed several runs for these simulations, all from 1980 to 2015, in which the main one is the iodine salt-based simulation, including iodine emissions and biogenic bromine very short-lived emissions. We have also run a no bromine very short-lived run in which we have removed the biogenic bromine very short-lived emission. This is just to take into account for the difference between for the effect of these biogenic bromine emissions. We have also run an IPART run in which we have enabled the particulate iodine implementation, although we are not going to show the result here, and a no iodine run in which we directly disable the iodine emission. And this is the simulation that we use as a blank to compare with the iodine simulation. We have employed the iodine simulation as a base simulation based in the vertical profile that we have calculated, which is shown here in the back of the bottom of the slide. Taking into account this vertical profile or normalized iodide photolysis rate average during the year 2000 within the extrapoles regions. We have based this calculation on theoretical calculations to define the energy threshold for the photofermentation from iodide particles back to the gas phase and experimental absorption spectrum to iodide. We consider these simulations with all the iodine in gas phase to be the simulations, due to the fact that we consider that based on these calculations, all the particulate iodine as iodide will be photolyzed back to the gas phase in his way from the lower part of the stratosphere to the upper part, and also to the poles, and being transported from the tropics to the poles. Here we are showing the results of the simulations. This first one is the 1990-2015 September-October average influence of iodine chemistry on the Antarctic stratospheric ozone depletion. The first one is the percentage impact over the stratosphere in the vertical column. This is the stratospheric column, the effect of ozone, in which we can see that it reached 3% at 90-70 degrees south. In the B panel is the effect at 100 pascals, in which we can see that the effect is up to 11%. And here we can see in the C panel, we can see an average meridional slice cut at 0 degrees longitude, in which we can see the effect of iodine chemistry, especially as a function of latitude and altitude, reaching up to 11% effect on ozone. In this plot, in the right, what we are showing is the impact of iodine in the ozone vertical profile, average in September and October in the region commented before, in 90 to 70 degrees south, during the whole period, the 1980 to 2015. This one is the vertical profile, and the B and C panel are the absolute and relative impact of iodine on the ozone stratospheric vertical column, in which we can see that the impact can be up to 4.25% on the stratospheric vertical column. This simulation that we have performed using iodine slightly improves the previous simulation using the WACAN state-of-the-art REV-C1SD. As we can see in this plot, in where we show the ozone average evolution of the total column ozone in Antarctica, together with the solar backscatter, ultraviolet instrument measures of Humboldt. We can see that during the whole time period, our simulation slightly improves the standard WACAN simulation, without the iodine chemistry, closing the gaps between the simulation, the standard simulation, and the measurements in all the period, except perhaps in the 90s, in which it seems that our simulation is destroying more ozone than previously thought, that expected, perhaps due to the eruption of Pinatubo volcano, which makes the SAT field not be perhaps perfect with the rest of the simulation. In this slide, what we are showing is the daily evolution of the ozone hole during the whole simulated period. This first one plot is showing the average ozone abundance at 11 to 16 kilometers altitude in the region 90 south to 70 degrees south for the simulation with and without iodine. The simulation with iodine is the red one, while the simulation without iodine is the blue. And in red, we are showing the difference in percentage, the relative difference, in which we can see the higher difference is 11% in the spring, in the month of October, due, of course, to the cross cycles, the interhalogen cross cycle between chlorine and iodine, and the general destruction of the destruction of ozone in the whole Antarctic stratosphere previous to the ozone hole. Here, what we can see in the B panel is the evolution of the ozone hole area, defined as the region of ozone hole between 200 and 15 top zone units, in which we can see in this plot, we can see again in red the iodine simulation, and in white, the simulation without iodine, that the implementation of this scheme advanced the formation of the ozone hole in something like 5 days and delays the closure of the ozone hole in 3 or 5 days. Here in this plot, what we are showing is the area of the simulation with iodine, which is shown here in yellow, and the expansion of the ozone hole area caused by the iodine, which is depicted in green, in which we have an expansion of 11% of the area, or 1.2 million kilometers. Here we are showing the relative importance of, the contribution of iodine chemistry to the evolution of the ozone hole in terms of ozone loss rate. In these first panels, what we are showing is the monthly average relative contribution of each family with respect to the total halogen ozone loss rate during the Antarctic summer. In January, which we can see an effect or a relative contribution of iodine of about 70% compared to the rest of halogen, and in spring, in October, when we have a contribution of something like 8%. In this panel, in the middle panels, what we are showing is the daily ozone loss rates compared with the rest of family, in which we can see that iodine contributes about 5%, 8% during the spring compared to the total ozone loss by chlorine and bromine. But in summer and at the end of the spring and summer, the contribution of iodine is up to 12%, reaching up to 25% during the months of April. Here in the panels of the bottom, what we can see is the iodine absolute and relative ozone loss rate average in these regions for the different channels, in which we can see that the main contribution of iodine is through the photolysis of IO and the reaction of iodine with bromine. But from June to October, what we can see is that enhances one increase in the channel of iodine with chlorine, which even surpassed the contribution of the photolysis of ion. Here in the relative plot, we can see more or less the same. The plan with the channels of chlorine with bromine making an effect in the winter and spring, when we have concentration of chlorine in the ozone hole in the Antarctic stratosphere, in the lower Antarctic stratosphere. And finally, what we have done to show the importance of the interhalogen channels of iodine and bromine is to make a sensibility in which we have removed those channels, so that we can see that if we have a simulation or the contribution of a simulation with iodine, the reduction of ozone is about 16%, while when we are removing the contribution of these interhalogen channels of iodine with bromine and chlorine, the reduction in ozone reaches up to 11%. So this 5% points difference is the contribution of these channels to the Antarctic destruction of ozone during spring. So summarizing, we have that iodine atom catalyzed ozone depletion has been neglected in the research of Antarctic ozone holes in this discovery due to the negligible amount of iodine previously thought to enter the stratosphere. iodine contribution to the ozone station and Antarctic ozone hole have been potentially significant, of course, particularly in the lower stratosphere, so we can see. Iodine destroys ozone in the Antarctic stratosphere through the photolysis for OIO, the reaction of iodine with HO2 and the reaction of iodine with bromine during the whole year, but also during spring for the reaction of iodine with chlorine channels. And of course, these results suggest that iodine injection and chemistry needs to be considered in models along with chlorine to have fully assessment about and projection of iodine-mediated impacts on the background ozone, abundances and ozone depletion in the Antarctic stratosphere. And this is all. Thank you.
Great, thanks, Carlos. Definitely nice motivation for iodine. Does anyone have any questions? I have a question. I was struck by you showed that with iodine, the size of the ozone hole is even larger in the simulation. I wonder if you also looked at the vertical profiles. Do the iodine reactions happen at the same altitudes as the chlorine and bromine, or is there an expansion over is there any difference in where it happens in the vertically?
You mean to the vertical distribution or the vertical special of the vertical? I mean,
so yeah. So it does. Well, yeah. So this shows that it's makes a difference in the size, but then
yes.
Your previous plot on the zonal mean that shows the vertical distribution. Do the iodine reactions occur the same place that the chlorine and bromine do? Does it all happen? It's all, is there any change in?
No, mainly the effect of iodine is in the lower part of the stratosphere, because this in this part where the concentrations of CLO and IO and the temperature gives this reaction. So it is not in the same part as the reaction with chlorine and bromine. It's most located in the lower part of the polar of the Antarctic stratosphere.
Oh, okay. Oh, interesting. Anyone else have some questions? Simone.
Oh, just following up, since you said it is mostly in the lower stratosphere. Why is that? Is that because of, why did you explain it? Sorry if I missed it.
Yes, this is where the most important effect is occurring, and this is between 11 and 16 kilometers, where are the part of the stratosphere where the concentration of IO and CLO are more important, and also the temperature, so that these reactions can take place here and not in the upper part of the stratosphere.
Oh, okay, sorry, I missed that, I guess. Thank you.
Okay.
Great. Anyone else? Kristen.
Hi, thanks for the nice talk.
Sorry.
Yes, thanks for the nice talks. The iodine chemistry, will that, or is that standard, or will that be standard for the CSM-AMWG model or the CSM model?
It's not completely standard at this moment. We are working on a version that we are planned to release during this year, so that it will be part of the CSM model. But up to now, we are still making several tests to make it available to the whole community. Up to now, we are using our version, but it will be released during this year.
Is there any time planning for that?
I cannot say at this moment. I understand and I know that at some point during this year, but I cannot say at this moment.
Thanks.
Welcome.
Yes, it's high on our list as soon as everybody's ready to release it. So it's an active area of development. Well, there's a lot of interest in it. Okay, if there are no more questions, then we can move on to Doug's talk. Doug Kinnison will continue talking about halogens in the upper stratosphere.
Okay, here, let's see. All right, do you see that, Louisa?
Yep. Perfect.
All right, well, yeah, so we started the first talk in the troposphere. We were in the lower stratosphere, and now I'm going to look at halogens in the upper stratosphere. This is a collaborative effort with the JPL group. We have a paper right now in ACPD on this topic. Lucian Frodovo is the lead on that. And we have a couple NCAR people. We have Chuck Bardeen, who helped with the simulations. We're comparing WACM to the MLS data. And John Orlando, who gave us some insight on some reaction rate constant information. So getting started on this. So what we're going to do is we're going to look at the 2005-2020 MLS period. We're going to look at the trends in CLO and HOCl in the upper stratosphere. And we're going to compare those trends to the WACM-6 specified dynamics nudge Tamara 2 model that was described in Gettleman et al. 2019. Chuck, that version of the model, I think, ran through 2014, and we've now extended that through 2020. Of course, everybody probably knows about the Aura satellite and MLS instrument. It's a limb sounder microwave. It gets about 3,500 vertical profiles per day, and you can get daytime and nighttime data from that. And then the model we ran from 1980 to 2020, as I just said, nudged Tamara 2. And one thing to point out is we do have pretty good halogen information at the surface up through 2014. After 2014 through 2020, we use the SSP 2-85 forecast for the halogens and CO2, methane, et cetera. What we do different than most studies is we actually sample the model like MLS samples the atmosphere or measures the atmosphere. And so for the given viewing locations and local times, we get profiles. We take those profiles, we bin them up in 5-degree latitude bins. And we even break that down by daytime values if the solar zenith angle is less than 90, or nighttime values if it's greater than 100. And so I'll show some results of that. Okay, so to kind of put this in context, I made this figure yesterday, which shows in the model world what the total inorganic chlorine would look like at 3.6 hectopascals. So, you have your organics that release all the chlorine at the surface. Eventually you get up into the stratosphere, and they fractionally release, depending on how they're blown apart, and they're inorganic chlorine. And this is what the inorganic chlorine looks like. We call it CLY, and the definitions above, and CLO and HOCl are currently part of that definition. Since the peak in CLY in the mid-90s, we're currently down about 14% of the total. When the Aura launch occurred in mid-2004 to present day, we're down about 10%. That's about 0.65% per year. So kind of remember that number. That's the change in CLY we would expect to see in the CLO species and in the HOCl species if everything is linear, and if there's not other constituents that are affecting the trends in these species. So that being said, where are these species located in the atmosphere? This is again model world, and you're looking at the near global mean, 50 south, 50 north of the main species that were shown in the previous CLY definition. This is from a 16-year climatology. This is daytime only results, so solar zenith angle less than 90. And you can see that CLO is the second most important gas in the upper stratosphere compared to HCl. HOCl is third. In the lower, in mid stratosphere, around 10 hectopascals, chlorine nitrate starts to become important. But these are important gases, and so it'd be interesting to better understand their trends. So the first thing I'll show is the climatology, and it'll be for January and July. Left is January, right is July. And this is for the 16 years. These are daytime values. The top row is MLS data, the middle row is the model, and the bottom row is the ratio of the modeled MLS. And in general, we have pretty good agreement in the magnitudes. We're within about 10% in most places, maybe up to 20% in a few. And considering all the uncertainties in retrieving these species and uncertainties in the amount of CLY that comes up into the model atmosphere from the surface and up into these levels, this is really good agreement. And so we're pretty pleased by that. So if I just go forward. Okay, yeah, now if I look at the CLO trends, so I skipped a slide there. Okay, now if I look at the CLO trends, first, the type of trend analysis we're doing is we're doing the typical multivariate linear regression approach. And if you want to read about this, you can go to Frodovold et al. ACP 2019. This is a paper that we wrote to evaluate the CCMI version of the model, or CSM1 WACM4. And all the error bars are going to be the 2 sigma uncertainty. And essentially, we're pulling out the linear trend term from this equation. So this equation takes into consideration the QBO, the ENSO, the solar, annual and semi-annual variations. And the residual is this linear term. And that's what's plotted on the left. And this plot goes from 1.5 down to 31.6 hectopascals. It's latitude cross-section. And what you see there is actually a pretty remarkable comparison between model and data. And it's all decreasing at, something a little under generally 1% per year. So we found that to be excellent agreement and showing that CLO is decreasing with time. If you look at the vertical trend of that, again, near global, you see the MLS data is in blue, the model's in red. And if anything, the model might be a little bit more negative than the observations, but it's certainly not statistically significant differences anyway. The MLS trends somewhere between minus 0.7 to minus 0.8 in the 15 to 1.5 hectopascal range. And remember, in my first slide, I said that the total CLY was going down about 0.65%. In the upper stratosphere. So this is a little bit more negative than what we think the forcing could be. Let's see, the model trend's a little bit more negative. It's about 0.9% per year. In general, very good agreement. Okay, how about HOCL? Again, the left is January for the climatology and the right is July. These are daytime averages again. Top row is MLS, middle row is model, bottom row is ratio. And one note about the MLS product for HOCL, it's a difficult retrieval. So they found that the best way to retrieve MLS is to not do the normal level 2 approach, but actually to take the radiances and average them in a zonal mean sense and then do the retrieval. So it's an offline product in a sense. And what you see in this comparison, if you look at the ratio, you see that the model is about 30% lower in magnitude for the climatology in both seasons, both January and July, than the observations. So there is a bias there. Part of this, in talking to Lucian, can be just due to the difficulties in retrieving this product and uncertainties within that. But it also can be the choice of the forward reaction for the formation of HOCL, the HO2 plus CL rate constant, basically. And this is where we discussed this with John Orlando, our lab kineticist in ACOM. And he found a reference, a more recent reference than what was included in the JPL 15 by Ward and Raleigh. And it has a larger rate constant, therefore a faster rate of forming HOCL. And this is an example for 1 year where we ran a sensitivity test. And the JPL 15 is in purple on the left there, and the Ward and Raleigh's on the right. And for this average, you can see it can increase the amount of HOCL in the model world from about 45% at 10 hectopascals up to 25% at 1 hectopascal. So there is an uncertainty there in the rate constant. There's uncertainty in the retrievals. So you have to keep that in mind when you compare these biases. Okay, so in this figure, this is the trend analysis, and this is for HOCl, but we've also added CLO to this figure. Again, near global, 50 south to 50 north, daytime averages, and the MLS data is in the blue, models in the red. The squares are CLO, and the circles are HOCl. And interesting, unlike for CLO, at the top of the pressure range there, HOCl does seem to be less negative in the data than it is in the model. And we don't really know exactly why this is so. But you know, I can talk about this briefly in the next coming slides here. But another thing you see with HOCl is the trend is actually less than CLO. The HOCl trends are on the order of 0.4 to 0.5% in the stratospheric range, and then CLO is again between 0.7 and 0.8%. So in kind of my big summary slide here, what I'm showing here is a trend of not only the species we just talked about, HOCl and CLO, but also CLY, HCl, and chlorine nitrate, and all of those are decreasing. But as a reference, if you look at CLY at the very top, again, that's about 0.65, and the open circles are model, filled circles are MLS, and the X's we've even added in some ACE-FTS data. So we don't measure total CLY, but the model saying again 0.65. HCl is something similar to that. It is interesting, and I'm not sure I understand why, but ACE is quite a bit less than HCl. It could be a sampling issue. CLO tends to be a little bit greater in the model and maybe a little bit greater in the MLS data than the CLY that's inputted in the model. The HOCl, however, MLS is about 0.5. The model is greater than 0.5, so there's a difference there. All these have overlapping error bars, so they're not probably statistically significant in any manner, but all the trends are decreasing. Chlorine nitrate's decreasing the least between model and ACE data there. And we put other species down in the lower right corner. They're actually increasing. HOCH is increasing in the form of HO2 and OH. Water's increasing, methane's increasing, NOx is increasing in the form of NO2 and NO. And N2O, the source of NOx, is also increasing. So these sources in the lower right corner can affect the partitioning of the trends in the upper left corner. And this has been discussed in previous studies, but for HOCl, it's proportional to the HO2 and CLO abundance. So if HO2 is increasing, as it is in the atmosphere based on briefly a little bit by aura and a little bit by the model, you expect that the HOCl trend will be a little bit less negative than it would be for CLY. For CLO is proportional to HCl, proportional to water to the square root power, essentially OH, and divided by methane. So they kind of counteract each other. So if water increases, the CL trend will become less negative. If methane increases, it becomes more negative. And so these things can play on each other and affect the trend. And Lucien Frodeval has a nice paper in year 2000 that really looks at these ratios, and he was comparing to UR's data. So if you're interested, I think it's a JGR paper that you could look at. Chlorine nitrate, as NOx increases, you're going to tend to increase chlorine nitrate, and so that will decrease the trend. And so we do see increases in NOx from NO and NO2. So all this is interesting, and so kind of in summary, CLO, the model climatological values and time series are very similar to MLS, and they agree, actually agree quite well. The trends are also very similar. HOCl, we have that bias issue, 20 to 40% low, but there's a lot of uncertainties in the retrievals, and there's uncertainties in the forward reaction that we're modeling, and so that bias can go away. The HOCl trends tend to be a little less negative than the CLO trends, most likely due to the formation reaction having more HO2. And then this is essentially a confirmation of the success of the Montreal Protocol and its amendments. So, you know, it's great to see that you have an instrument like the Aura MLS instrument that takes data for 16 years and can really monitor the change in these important species that affect the ozone layer. And so on that, I think I'll end. Thanks.
Right. Thanks. That's a lot of really interesting work. It's nice to see Wacom doing so well. We're running a little late, so if you have questions for Doug, please type them in the chat and maybe he can answer them there, and maybe, or if we have time at the end, we'll come back to those. And so we will move on to Michael Weimer, who will discuss stratospheric chemistry, impact of subgrid scale gravity waves. As soon as Doug stopped sharing.
Oh, yeah, sorry.
Looked like you were
there we go. How's
doing that? Yes, that's good.
Thank you. Can you see everything?
Yes, looks perfect. Thank you.
So thank you. Thanks a lot for the introduction, for the opportunity to speak here today. I want to give an update about our project, about the stratospheric chemistry impact of subgrid scale gravity waves. And as you can see, some of our colleagues, Ed and Carl, are also included in this project. Why do we even care about gravity waves and the interaction with the chemistry? As you know, gravity waves are really important in the sense that they are responsible for the middle atmosphere, for the dynamics in the middle atmosphere, but they also lead to temperature perturbations. And especially if the air parcel is lifted, it leads to a cooling of the air parcel. And it was found that this cooling can be in the order of 10 to 15 Kelvin in the stratosphere. So there's a significant cooling in the stratosphere, which is locally confined. And by that, of course, the chemistry is impacted because the chemistry is really sensitive to temperature perturbations. In addition, there's the effect that in this cooling part of the gravity waves, locally polar stratospheric clouds can form and then lead to even higher heterogeneous processes in the atmosphere. This was found in observations, but it cannot be simulated in the sense that it's really locally, that these polar stratospheric clouds are created locally. And as you know, the most fraction of gravity waves, or the most fraction of the spectrum of gravity waves, has to be parameterized in the current chemistry climate models. And there wasn't any possibility to account for this direct effect of gravity waves in the chemistry. And this is kind of the idea of our project, because we can transfer some quantities from the gravity wave parameterization to the chemistry. For example, the vertical displacement of the air parcel, or the vertical gradient of the potential temperature, and then derive a temperature perturbation due to subgrid scale gravity waves in the chemistry, which we then can use to account for this process. And as you can see in this figure here, we use a chemistry subcycling where we use T prime as an amplitude of a sine wave. So we have the Wacom physical time step of half an hour here, and it's divided by a factor of 10 in this case. So we use a time step of 3 minutes in the chemistry, where we use the green dots essentially as the temperature input for the chemistry. So by that, we can actually account for the process of subgrid scale gravity waves in the chemistry, which was not possible before. And just to give you an overview what this subcycling looks like, we compute this T prime value, then polar stratospheric clouds are created and the heterogeneous reaction rate constants are calculated. Then the gas phase reaction rates constants are calculated, followed by the photolysis rates, some external forcing and washout rates. Then the chemistry solver is all obviously included in this chemistry subcycling, followed by the gas aerosol exchange and the PSC settling. So this gives you an idea how this is kind of implemented in the model. And as I said, we used the WACHM 6 model for this with the FWS decomp set, which uses specified dynamics, which basically means that the dynamics are relaxed towards MERA2 up to 50 kilometers. The horizontal resolution in this simulation is about 1 degree, and it has 88 vertical levels up to 150 kilometers. We performed 2 simulations. One is the reference simulation without any subcycling, and the second simulation is the simulation where we applied this new parameterization, which we implemented for orographic gravity waves only at the moment. And this is why you can see on the right-hand figure here that T prime, this is the global distribution of T prime, that it's kind of that you can see the mountain regions in this global distribution. It's at 52 hectopascals for a specific day of July 2011, and since it's the southern hemispheric winter, especially the southern hemispheric hotspots of orographic gravity waves are especially highlighted with high values of T prime, like the Andes region or the Antarctic Peninsula. But before we can even start to look into the chemistry impact of this new parameterization, we have to evaluate our T prime values with measurements so that they are at least in some kind of realistic range. And for this, we use the cosmic data. So these are GPS radio occultation measurements with a vertical resolution of about 1 kilometer. They are reliable between 10 and 38 kilometers. So we can especially look into the lower stratosphere where we are most interested in. And the great thing is that cosmic measures temperature profiles with a almost global distribution coverage, so that you can use methods like that of Wang and Alexander 2010 to derive T prime from only the measurements. And by that, we can actually compare T prime with that of WACHM. WACHM, as you know, excites monochromatic orographic gravity waves, which means there's no dispersion or lateral propagation of gravity waves. And this means that the amplitudes of gravity waves could get really large in the stratosphere. And this is why we wanted to look if there's a scaling needed for the T prime values before we actually can look into the chemistry impact. So what we did is that we compared the distributions between cosmic and WACHM, and the answer is yes, there's a scaling needed, and you can see that the scaling depends on the latitude region, on the altitude, and at the moment also on the season. And especially during in the lower stratosphere, you can see that scaling factors are lower than 1, which means that the T prime values have to be reduced so that the distributions between cosmic and WACHM are kind of similar. We are currently looking into the scaling if there are better ways to do that. And we also want to look into further data like mesoscale models that are around, like WRF, or reanalysis data to compare our T prime values with other data. So this is a first comparison and the first scaling of T prime. And now we can actually look into the chemistry impact. And I want to just show 2 short examples of the impact of this new parameterization. What I want to show here is the impact on polar stratospheric clouds in terms of monthly and zonal mean differences between these 2 simulations I mentioned, between with and without this new parameterization applied. And for example, for ice clouds, you can see for this specific month of June 2011 that the ice particles are increased in the tropical tropopause region. So in the region where we have the largest, the lowest temperatures, and they are also increased at the edge of the polar vortex, which you can see in this temperature distribution. This means that especially the temperature decrease of the gravity waves leads to an increase in the surface area density of ice clouds in the tropical tropopause region. And in this region at the edge of the polar vortex, the atmosphere is quite sensitive to temperature perturbations, and this is kind of reflected in ice clouds, as you can see here. We also can see that sulfate aerosols are increased at the tropopause region. We are currently looking what is the process that increases this sulfate aerosols, but as you can see, polar stratospheric clouds are increased, and of course this leads then to has further implications on other species. And I just want to give you one example of the active chlorine species. You can see here the differences in this same kind of figure for ClO, Cl2O2, and chlorine nitrate. And you can see that as expected, ClO is increased at the tropopause, where we also saw this increase in polar stratospheric clouds. And especially for Cl2O2, you can also see that it is increased in this region with large temperature gradients at the edge of the polar vortex. We also see a decrease in chlorine nitrate in this region, which is kind of clear because it's activated. And but these are kind of preliminary results because we have to look into some technical aspects as well before we can do the actual analysis. So to conclude, we have developed a method to account for subgrid scale gravity wave temperature perturbations in the chemistry, which can be applied globally, and this was not possible before. I showed a first evaluation with cosmic T prime profiles so that we can be kind of sure that T prime is in the right range of magnitude. As I mentioned, we want to look into further data like mesoscale models and reanalysis data to be even more sure that our T prime values are in kind of realistic order of magnitude. And I showed just the first impact on the chemistry, like increased surface area density of polar stratospheric clouds, especially for ice and sulfate aerosols. And this leads kind of to increased active chlorine species, especially at the large temperature gradients, which is interesting to see. And of course, in the future, we also want to evaluate this chemistry impact with measurements. And I want to acknowledge the funding of this work by NSF, and thank you. Thanks a lot for this, for your attention, and I'm happy to take any questions.
Great, thank you, Michael. That was very interesting. Are there any questions?
I would like to ask a question.
Go ahead.
So in your, this is Ring Chen, hi.
Hi.
In your gravity wave temperature fluctuation plots, it doesn't show much impact in the tropical region. It has lots of temperature fluctuation in the high altitude, high latitude. I just wonder, how could it have such a big impact on the ice nucleation in the tropical region?
So this was one specific day in this distribution of T prime in this figure. So we see impact for other days, for other months, and this is what explains this. I think.
Okay, thank you.
Great, thanks. Well, in the interest of time, I think maybe we'll move on. If people have more questions for Michael, feel free to put them in the chat. And we will now move to the troposphere. And the next talk will be by Ben Gobert on trends and variability of carbon monoxide.
Right. Do you see my screen? Can you hear me well?
Yes, that looks great.
All right. So I'm Benjamin Gobert. I work at AECOM here at NCAR. This is a work I've been doing with Kavita, has been doing a virtual visit funded by the ECSA. Move on. Next one. So we're using the MOPIT CO, and we're using the new version 9 retrievals that includes those retrievals include significant improvements in retrieval coverage over a polluted region, as you can see here, by doing retrievals in over scenes where there are potentially aerosols. And there was a significant revision to the NIR calibration, which should improve the temporal consistency. Because the context is that over a large band of the tropic, if you look at anomaly relative to the global average trend, there is an apparent increasing in CO column. And because the CO is not declining as fast as at the beginning of the MOPIT record, and this could be due to many things, chemistry, the fires, and anthropogenic sources. And so we wanted to have a look at trying to understand what are the reasons behind those features. So the idea is to use the STL method, is to decompose the time series into a trend and a seasonal component using an additive method. Here I'm doing it twice, where I'm doing first the calculation of the trend and with the low pass filter to calculate the interannual variability. And then I'm doing it again to get the seasonal cycle. So I'm doing first the long-term trend and second the short-term trend, which is the interannual variability. So I used that in my study in 2017, where we showed that the decrease in CO in the tropic is leading to an increase in CO chemical production, and so there is a positive trend in secondary CO while the primary source is decreasing. And that's because of the feedback through OH. And so here's the trend component. You can see that the trend in abundance is very well correlated with the trend in methane lifetime. And so if you look at the seasonal cycle, the CO chemical production is driven by the isoprene emissions, primarily, and secondary by the methane chemical loss. So based on that decomposition in the budget, we were thinking that we could try to do more of these to try to understand what is going on in the MOPIT record. So here are the results for MOPIT for the 20 years period from 2001 to 2021. And this is for the Northern Hemisphere extratropics. We can see a decreasing trend that is very pronounced in the beginning and then a bit slower in the second part of the decade, with pretty significant interannual variability, very large seasonal cycle too. that is also changing. And here is what we may be more interested in is the reduction or the reversal in the trend in the southern hemisphere tropics. And so there is obviously the large features of the fires, but there are other things that we don't quite understand really well yet, which is a decreasing seasonal cycle. So here is my an example of the simulation if I apply the STL to the CAMS emissions. The CAMS emissions are based on NGAR until 2015, and then it's just linearly extrapolated based on the CESM emissions. So you can see that feature pretty well, where there is pretty large decrease in emissions and then pretty stable emissions second part of the period for the northern hemisphere industrialized regions, but an increase in the emissions for the tropics. So we have that in a simulation with QFED and MERA2, trying to look at the 20 years period. And then I did the same simulation, but with repeated emissions for 2020. But with increasing the varying greenhouse gases, so an increase in methane and a biogenic response to meteorology. But both simulations are with specified LEI. So here's are the results. So for the northern hemisphere extratropics, if you look, the trend baseline is your baseline, your CO, and that is reflecting the anthropogenic emissions as has been hypothesized in different studies, and but also biomass burning could play a role if there is a trend in biomass burning. Here in the simulation with constant emissions, you can see that there are virtually no trend or slightly increasing trend that could be due to the increase in greenhouse gases, methane oxidation to CO. But if you look at MOPIT XCO, you can see that we are underestimating that decrease. So that's something to take into account, but and to evaluate that quantitatively in the future. If you look at the seasonal cycle, so here I'm doing the MOPIT column, no, the model column, sorry. And then I'm doing also that for the QFED tag and the CAMS tag. And so those are 3 different STL based on the same simulation, with and without constant emissions. And it appears that the seasonal cycle of CAMS seems to be playing an important role in the seasonal cycle of the model CO, with very similar amplitude, while the QFED is important, but much smaller in this case of the average of the whole northern hemisphere extratropics. But it's important to recall that the chemistry is very important. The seasonal cycle is driven by the chemistry and the cycle in OH. It's just that they both happen to be have the same sink. So now if we move to the southern hemisphere tropics trends, in this case there is no clear impact of the emissions, and so could be the methane oxidation is increasing, and it's more work need to be done to show some later. Here's for the MOPIT record. That doesn't show any trends, and the related seasonal cycle. And so this is a seasonal cycle for the model, where we're trying to disentangle the different drivers. And the biomass burning of QFED is responsible for the seasonal cycle, but the CAMS is also leading to increasing CO in the winter months, which seems to be reflected in the record. In as well as MOPIT with that double peaking. But there is the decreasing CO cycle then seems to be explained by the model by the decreasing QFED emissions, which is not the case in the constant emission one. And here is the MOPIT seasonal cycle. So what we did next is to calculate the budget, the CO burden. So in the model space for a given region, and to calculate the correlation with, like for instance, here the trend component with the emissions, anthropogenic emissions, anthropogenic CO burden, so the CO tag, QFED CO emissions, QFED CO tag, the megan CO, and chemical fluxes, sources and sinks of CO. And so, for instance, for the trend in the southern hemisphere tropics, there is a very strong correlation of CO with anthropogenic sources, megan CO, and chemical oxidation, and overall chemistry, but decreasing correlation, negative correlation with the biomass burning. And I think this is due to the fact that the CO is increasing, but the biomass burning QFED CO is the only trend component that is decreasing, while all the other ones are likely to be increasing. So if you look at the seasonal component, then in this case, the biomass burning is playing an important role. But also emissions and chemistry is actually, again, the methane oxidation is important in that region. So all of this is work in progress. There are some things that I was a bit surprised, is that the importance of the anthropogenic emission seasonal cycle on the CO seasonal cycle in the northern hemisphere. Where I thought it would mostly be playing a role in the long-term trends. The fires are also playing a role in the interannual variability, so that's less of a surprise. And MOPIT is showing, according to this method, a declining seasonal cycle on average. But for the tropics, it's actually difficult to really disentangle the different sources of temporal variability, because the internal variability could be due to interannual variability in La Nina, which is more a cycle that is 5 years and not 1 year, and so the change in seasonal cycle could be impacted by that. So we're gonna try to do more, compare different methods to assess that. The megan biogenic emissions and the fires emissions contribute to the seasonal cycle and the internal variability components, while the biomass burning is negatively correlated for trends, probably because the QFED emissions are decreasing. And the CO chemical production is increasing, so the secondary CO trend is related to the methane oxidation increase. So for future work, we're gonna do an actual quantitative comparison with MOPIT for the different regions and the different temporal components. We already started to look at CAMS reanalysis and the NOAA global network of the surface in situ measurements that show very similar features. And we're gonna evaluate carefully how we do the trend and the seasonal cycle estimations by comparing with other methods. And that's all I have. I'm happy to take questions.
Thank you, Ben.
Thank
You could turn down your volume. It's a big echo.
Oh. Oh, yeah.
We're rather out of time, but is there a quick question? Anyone have a question? That's an impressive amount of work. It's nice to have so much long time Moppet record to do this analysis with. So it's really great. If you have any questions, type them in the chat. We seem to have a nice discussion going on the previous talks in the chat. Sorry, there's not more time to do that in person, but we'll move on to our next talk by Danny Lung, who will tell us about some improvements to the dust emissions scheme, a new scale respecting parameterization for desert dust.
Okay, hold on. Let me share my screen.
Great.
Okay. I hope you can see my slides right now.
Looks perfect.
Okay. So, hi, good morning. I'm Danny. I'm a fourth-year PhD student from UCLA working with Professor Jasper Cook on dust modeling. We are collaborating with Dr. Lung Lei and Professor Natalie Mahowal at Cornell. And we also have Dave Lawrence, who is my ASP host at ANCAR. And we have more collaborators. And today I'm going to talk about our development on a more process-based and realistic dust emission scheme for GCMs, and specifically CESM2. So the reason we need a better dust emission scheme is because dust is contributing to a great uncertainty in atmospheric radiative forcing and climate change projections. And accurate GCM simulations of dust is vital for the accurate climate change projections. But as you can see, model dust does not capture the satellite dust spatial variability very well. CSM has a much larger dust AOD over the major source regions compared to the satellite retrievals such as Africa, Central Asia, Australia, and so on. Also, studies show that the GCM's dust simulations are not sensitive enough to climate and land use line cover changes. And this is because many aeolian processes are not yet included in the GCMs. Therefore, in this study, we are adding more aeolian processes into CESM2. The first one is to add that Cook et al. 2014 dust emission scheme into CESM2. It is a much more process-based scheme compared to the default standard scheme in CSM. Cook's scheme has been added into CSM1 before, and very recently it has been examined in CESM2 again. We are adding in the latter four modifications on top of the Cook et al. Scheme. The first one is the effects of soil particle size distributions to the dust emission threshold wind speed. The second one, it's the wind drag partition effect by rocks and plants over desert surfaces because of the wind momentum absorption. The third one, it's the dust emission intermittency effect due to the boundary layer turbulence. And the last one is to implement a correction map for coarse gridded GCMs to account for the high resolution dust emission spatial variability. So the first modification, it's about dust emission threshold wind speed. In dust modeling, the wind speed needs to exceed a certain threshold wind speed in order to trigger dust emissions. The dust emission threshold wind speed depends on the soil particle size and soil moisture. And for the soil particle size, CSM assumes a globally constant 75 micron, which is known to be unrealistic and uncertain, but nobody has used observations to get a better estimate or constraint. Therefore, we dig into the past literature and examined multiple soil particle size distributions across the globe. And we found that over the arid regions here, which are the red data points in the left graph, in situ median soil particle diameter have a mean of about 130 micron, which is much larger than the 75 micron assumed by CSM. Moreover, the median diameter has relatively small variability across arid regions. Therefore, we can replace the globally constant 75 micron by another globally constant 130 micron in the CSM. And this leads to an about 10% increase in the dust emission threshold wind speed, because soil particles are now larger and heavier to lift. The right panel here shows the global distribution of dust emission threshold wind speed after modifications. And it has the same spatial distribution as before, but just our modifications increased the threshold of the whole globe by about 10%. The second modification is called the drag partition or roughness effect due to plants and rocks over desert surfaces that absorbs wind momentum and reduce dust emissions. So the drag partition effect, F effective, we call it F effective, discounts the friction velocity, U star, reaching the soil surfaces to a smaller wind drag, we call it U star S. And F effective incorporates both effects of rocks and vegetation. For rocks, we use a time invariant aeolian roughness length dataset derived from the satellite measurements by Catherine Frijon. And for plants, we use Gregory Okin's scheme to quantify the drag partition using the time varying CLM leaf area index. We then combine the two roughness effects by a weighted mean equation approach using the land cover fraction of rocks and vegetation. The left-hand side graph shows the annual mean F effective, which strongly characterizes the major source regions, such as the Beaudelet Depression here, El Juouf here, Taklamakan Desert, and the Arabian Desert here. The drag partition effect now strongly shapes the spatial variability and redistribute the dust to major source regions. The third modification is to add in the dust emission intermittency effect. As we know, models use a large model time step, say half an hour, and assume a constant wind speed within the time step to calculate dust emissions. In reality, there are a lot of instantaneous and high frequency wind fluctuations within the time step that can cross the emission threshold multiple times within a model time step and shut off dust emissions intermittently. So we need to characterize the fraction of time eta that emission is active within one single model time step and multiply it by the dust emission flux. The fraction of time eta will be a function of the wind speed, the threshold, and the fluctuation strength. And the fluctuation strength is quantified by the Morning-Overkopf similarity theory here. And here we show the annual mean fraction of time eta. Even for major sources like Beaudelet Depression in Sahara, eta is about 80%, which means the local wind fluctuations are strong and can shut off dust emissions by 20% of the total time. So we need to scale the emission down to account for the shutoff. So dust emission is actually smaller than what was previously predicted by the model. And with all these process-based modification in mind, now let's take a look at the dust AOD of CSM2 using different schemes. So here we show the Cook et al. Scheme, which is different from the Sander et al. Scheme, the default one, and has much smaller dust AOD over Central Asia and Australia and South Africa. And it has a strong pile of dust over the Sahara. Our scheme adds further aeolian process on top of the Cook et al. Scheme, and our scheme has further reduced the strong dust over Sahara and Australia. However, our scheme for now still cannot show the clear localized dust sources over the Beaudelet Depression and El Juouf over Sahara, as clearly shown by the satellite. We have done some evaluations with AOD datasets such as AeroNet. We selected about 40 sites that are close to the deserts and mainly influenced by dust. And the evaluations shows that our scheme matches the AeroNet AOD the best, capturing the best spatial variability of dust AOD. Our scheme has a high R-square of about 81%, which is very close to the Modus Aqua's performance of 83%, matching against the AeroNet data. In contrast, the default CLM scheme, the Sander scheme, has only 36% of R square and has a very high root mean square error. We also demonstrate that our scheme captures not only spatial variability, but also the temporal variability. Here we show a seasonally and regionally averaged dust AOD dataset compiled by David Ridley for evaluation. Our scheme shows the highest R square again, capturing 86% of the seasonal and regional variability of the reanalysis DAOD. And this is because the drag partition and intermittency effects have coupled the dust better with the vegetation and boundary layer dynamics. So the dust now have a better temporal variability. And then in the next slide, we show the grid by grid daily correlation with the aqua dust AOD. And we can see that the main improvement from the Sander versus aqua to the Koch versus aqua here is that the correlation has strongly increased over the dust belt, including the Mid-Atlantic, Sahara, and Middle East. But the correlation over China has reduced, as shown here. The upper right shows the correlation for our scheme versus aqua. Our scheme has further improved dust temporal variability over the Boulderly Depression and El Juf here, as well as China. And this is because drag partition effects indicate Sahara and China to be the most erodible regions, strengthening the dust representation over Sahara and China. So now I talk about the last modification. It is not process-based, but related to the grid resolution. As we know, dust emission is very sensitive to the local scale wind extremas. So we simulate dust emissions in an even higher resolution of 0.5 degree, because we believe high resolution simulations give a better representation of the subgrid spatial variability of dust. So now by dividing the high resolution dust emission to the native dust emission of 1 degree for CESM2, we obtain an annual mean correction factor for the 1 degree CESM2. And then it shows that the high resolution dust tend to have more emissions over the marginal source regions and has relatively few emissions over major sources. And this is helpful to the 1 degree CESM2 because it has overestimated the dust AOD at major sources, as seen in this middle panel here. So putting this time invariant correction map into the 1 degree CESM2 and multiply it by the 1 degree dust emissions and simulate again, we can have further improved the dust spatial variability against the Ridley dust AOD data, as shown in the right panel, with a higher R square and a smaller bias. So to conclude, we have implemented more aeolian processes in CLM5 in CSM2 to further couple dust with vegetation dynamics and boundary layer dynamics. Our modifications yield significant improvements, especially for dust AOD. And we hope our improvements can let CSM better simulate the dust climate interactions and aerosol cloud interactions and improve the climate change estimates in the future. So that's it. Thank you. I'll take questions.
Great. Thanks, Danny. Yeah, this has been some very nice improvements to CESM. Julio had a question. Is there a maximum length scale or size assumed for rocks?
So we use a data set that is captured by satellite measurements, and it just quantify the local scale roughness length captured by the active scatterometer measurements. So the length scale, it's about, less than 10 kilometers. So if there is surface roughness, the satellite can measure up to about 10 kilometer relative changes and smaller scale than that. So it won't be able to capture the orography or topography that is very large scale and captured by the aerodynamic roughness length. So we're talking about small scale structures that are really relevant to the Iodine processes and dust emission here.
Okay, that's interesting. I mean, 10 kilometers to me sounds very big. I'm just wondering if anybody has compared roughness from this data with roughness from digital elevation models, because at 10 kilometers there seems to be quite a bit of overlap.
Well, I think it's up to 10 kilometers, but
Okay.
the resolution of the data is actually very small. It's actually smaller than 0.1 degree. So it's actually less than 10 kilometers. So I think it's up to, close to 1 kilometers or even smaller. But I don't think anyone has compared it with other data sources yet. But I know that this data is also entering into CESM to adjust its aerodynamic roughness length at the same time.
All right, thank you.
Great, thanks. In the interest of time, we'll move on to the last talk, and maybe we can come back for more discussion. So thank you. So the last talk is by Wenfu Tang, and she's going to show us her first results with Musica version 0 with a refined grid over Africa.
Thank you, Louisa. Can you see my screen?
Yep, looks good.
Great. Hello, everyone. I'm Wenfu Tang from NCA, and today I'll be sharing an ongoing project I'm currently working on, which is the application of Musica over Africa. So here's some background. Africa is one of the most rapidly changing regions in the world. The population is rapidly growing, and the urbanization is also happening very fast. And air pollution is a serious problem in Africa. And some recent studies have shown that the air pollution in Africa is causing serious health issues. However, the study of air quality in Africa is hindered by the limited in situ observations. As an example, the figure here shows the global particulate air pollution from the worst in red and to the best in green, and also the distribution of the national air quality monitoring network locations. And as we can see, the observations over Africa is limited. So modeling can be a very useful tool to understand the atmospheric chemistry, air quality, and their impacts over Africa. The multi-scale infrastructure for chemistry and aerosols enables the study of atmospheric composition and chemistry across all relevant scales, which is exactly what we need to look at Africa. So Musica version 0 is Chem with regional refinement, and the figure here on the left shows the default configuration of the Musica version 0, which has a refinement over the North America. And the Musica users have the option to create their own grid. And the figure on the right shows the grid I created for Africa. And thanks to all the helpful tutorials, recorded videos, and the step-by-step guidance on the web page, creating and running Musica with a new grid is not hard to do. And the grid I created here has a resolution of around 28 kilometers over Africa. So, so the simulation is conducted for the year 2017, and I used the Chem's version 5.1 for anthropogenic emissions and QFED for fire emissions. And in addition, I also include waste burning emissions that are downloaded from the ACOM website listed here in the list. And the model wind and temperature are nudged to the MERA2 reanalysis data. And to understand the sources of the air pollutant and their transport and also the regional impact, I included 18 carbon monoxide model tracers. So the CO tracers can track the CO emitted from different sources and regions. So 6 source regions are included, namely the Northwest, Central, East, and South Africa. And 3 source types are also included, namely the anthropogenic, fire, and waste burning emissions. So before looking into the model results, here I briefly compared the MUSICA to in situ observations and the results from a regional model, WolfChem. As we know, the in situ observations are very limited over Africa, and this comparison is preliminary. The slide here shows the time series of surface CO from MUSICA version 0 simulations compared to WolfChem and CO in situ observations at 5 ground sites from the World Data Center for Greenhouse Gases. And the black line is observation, the red line is WolfChem, and the blue line is MUSICA version 0. And as we can see, besides this CPT site, for all the other sites, overall, the performance of MUSICA is comparable to the performance of WolfChem in this case. And let's look at the MUSICA version 0 simulation results. Here I'm showing the seasonal mean of surface CO over Africa in 2017. And as we can see, the different subregions can have very different seasonal cycles. We will look into the drivers later using the model tracers. And here I'm showing the seasonal surface PM 2.5. There are a few co-located hotspots of CO and PM 2.5, such as those highlighted in these red circles. However, we can see the overall distribution of PM 2.5 and the CO is largely different. And this is because the sources of Africa is very complicated and mixed, and the regional variation can be large. And we will look into this later. And here I'm showing a regional and a monthly average of a few pollutants at the surface, including the CO and the SO2 and the NO2 and the ozone and the PM 2.5. Over the North Africa, all the 5 pollutants have different seasonal variations. And over the West Africa, the 5 pollutants shown here overall have similar seasonal variations, except that CO has a peak in August, which is similar to the CO peak for the North Africa. And as for the South Africa, it has significantly higher SO2 and NO2 concentrations than all the 4 other regions, as if you look at the y-axis here. And for the Central Africa, the CO concentrations is higher than the other regions. And the 5 species here have similar seasonal variations except for the PM 2.5. And lastly, over the East Africa, the seasonal cycle of NO2, ozone, and PM 2.5 are close to each other. And now let's look at the source contribution analysis with the model CO tracers. The figure on the right shows the CO concentrations contributed from different source types. And the light gray is fire, and the gray is anthropogenic, and the dark gray is waste burning CO emissions. Oh, and the dashed line is the total CO concentrations from the model. As we can see, over the North and the West Africa, anthropogenic sources is a dominant source for CO concentrations, and waste burning has a relatively higher contribution over the North Africa compared to other regions. And over the Central Africa, fire is a dominant source for CO. And over the East and South Africa, fire and anthropogenic emissions are both important, and the seasonal cycle is mainly driven by the fire emissions. And here is a more detailed source analysis for the source regions. The first row is regional, the first row is the regional contribution for total fire CO tracers, and the second row is anthropogenic, and the last row is the waste burning regional contributions. And overall, the local emissions dominate the CO concentrations for each region, and there are a few interesting points to notice. First, the North Africa is strongly impacted by the emissions transported from outside the Africa, as shown by the gray area. And over the West Africa, during summer, the CO emitted from fires in Central Africa are transported to the region, while during other seasons, the local fire emissions is more important. Here, over the for the South Africa, fire emitted from Central and East Africa transported to the South Africa has a large impact there. And here, fire and anthropogenic emissions from the East Africa contribute significantly to the CO concentrations over the Central Africa. So that's all the results I'd like to share today. In summary, we conducted the MUSICA simulations over Africa for 2017 with model tracers of CO emitted from different sources and regions. So the preliminary evaluation with surface CO measurements showed that MUSICA performance is comparable to WolfChem over Africa. And we will conduct further and more detailed evaluation against satellite data and more detailed comparisons with WolfChem results. And the model output is all freely available. And I saved much more variables that was more than what I just showed today. And if you are interested in looking at these results, or if you are interested in any collaboration, please feel free to contact me. With that, I'll stop here and thank you.
Great, thanks, Wenfu. Are there any questions? Certainly highlighted that Africa is going to be a diverse continent to study. Okay, if there are no specific questions for Wenfu, there's a lot of discussion in the chat about dust. I think it looks like Danny's been answering everybody's questions. Is there anything specific anybody wants follow up on? You can raise your hand. Or any outstanding questions from any of the previous talks? Mary.
So very nice talk, Wenfu, and I'm looking at this discussion between Dusong and Danny, and so I was wondering, Louise is laughing, it's like it's obvious, right? I was wondering if you looked at the dust emissions in your simulations with MUSICA. Wenfu, did you get that?
Yeah, so I don't know what's the timeline for implementing the new scheme from Danny to.
But did you evaluate the dust in the MUSICA simulations?
No, not really, but I'm planning to do so.
Okay. Yeah, it'd be interesting in the context of Danny's work.
Yeah, the simulations now is default. CESM still has the Zender scheme. But yes, that certainly will have impact. Simone.
thanks. I think if I remember correctly, you evaluated compared to WRF, the regional refined. Did you look at the 1 degree simulation? I'm not sure if I saw that. And if so, I mean, the question will be, why do we need a regional refinement? Is a 1/4 degree sufficient for those questions to be answered? I mean, it's great to have it, but I mean, what's, do you see advantages?
Yes, so I did not compare. Do you mean the 1 degree model?
Yeah.
I did not compare to the 1 degree model. So the WRF-Chem I compared was the 20 kilometer resolution, slightly higher than our resolution. So when I choose the resolution, I considered both the 28 kilometer and the 14 kilometer there, but I decided to run 28 kilometer first because we don't really need we don't have much information over the region yet, and 28 seems to be a good start point. I have not compared to a 1 degree model over Africa, so I'm not sure yet how large the difference will be. But I think as we get more and more information over the region and more studies going towards the direction, we will have more information, and a higher resolution simulation would be definitely needed there.
Yeah, one reason I asked was also that before we looked at air quality just with a 1 degree finite volume, and really when you are the places like Nigeria, Lagos, that are very close to the coast, you do not get the right answers with a coarse resolution for the land sea contrast and so on. So I would think that this could be improved. I would think, but that would be an interesting question. If you look more at those places, and there are data available too, that may be interesting to look at. Other data like IAGOS, no, what is it called? Yeah, from the aircraft data and stuff like that, to see if that changes or improves the situation.
Yeah, that's a great point. I will look at the coast regions and see if that makes a difference. Yeah, thank you.
Xiaohong has a question.
This question is for Danny. And so you said that the new dust scheme has a more closer coupling with the land model. I wonder if you could consider the dust from anthropogenic source, like from agricultural activity or something like that. Because of land use, land cover change.
Yeah. So our scheme currently only take care of the natural desert dust. So yeah, the only thing that human effects will enter into our dust emission scheme, it's about the line cover fraction, because we have defined our drag partition effect to be a function of the line cover fractions of rocks and vegetation. So if in the future there is any changes in that, say by deforestation and afforestation, then it will certainly change the pattern of dust emission too. But for now, our effect only works on the natural desert dust, not the anthropogenic dust.
Okay, thank you.
Yes, we need another graduate student or postdoc to work on that. Certainly an important dust source. Okay, we've gotten right to 10:55, which Elizabeth had said is our time to break and give people a few minutes before the CGD seminar. And so you should have seen in the email that the seminar will be it's all, the link's also in the agenda. It'll be streamed on the NCAR CGD YouTube channel. So Isla's going to talk about what should we expect for the future of North American hydroclimate. And then our working group meeting talks will resume at 12:15 Mountain Standard Time with some upper atmosphere talks. Thank you all for joining, and thanks everyone for all the nice